So last time we sort of did some examples on the per unit system, and we did one example where we had a star delta transformer, and Chatia said, okay, so why aren't we dealing with this differently, right? And I said, okay, that typically we will ignore the star delta effect because it does not really change what happens when we talk about equipment rating. It will really be something that will affect us when we talk about actual building of the system and building of or designing the protection system for a certain power system, because what the star delta transformer does is change phase shifts between the voltages on the primary and the secondary with respect to each other. So with these phase shifts happening, you need to make sure that the machines and the equipment you have in your system are connected in a specific way. You cannot just take a transformer and, okay, these are three terminals. That does not work that way because phase shifts will occur. And we will see today how that happens. Yeah. So in your homework, I think we have one example where you can create a weird number of phase shifts based on how you connect the windings with each other. So we will talk about the most famous ones here, the most commonly used ones here, and then you will have one example that's a bit more elaborate in the homework that gives you a feel of, okay, wow, I can do any phase shift I want between the primary and secondary, really, depending on how I connect the transformer windings. Yeah. So so we talked about the four different types of transformers that are typically used in a power system. YYs and delta deltas, as we said, they're typically not really used a lot. The most commonly used transformers are at the generating to step up. You typically use a delta to star transformer or delta to Y transformer. And then anytime you're stepping down, you're typically using a star to delta transformer. That's typically the most commonly used transformers. The delta delta transformer is interesting. So this is star delta and what delta star. Delta delta is what they say here is used for medium voltage. One of the transformers can be removed from an open delta. So let me sort of elaborate a little bit on that and continue. So sometimes come on, I don't want to put my Apple ID. Why do I have to put my Apple ID? Come on, don't let me down. It is letting me down. Serious? No, I'm not, but I don't want to. Why should I? Ah. Okay. I'll connect to the Wi-Fi. Sorry. Network. Where's network? It's already connected. It's connected or it is. Okay. Okay, so they were saying that medium voltage sometimes this delta transformer is used. They were saying because you can drop one of the phases or something like that. So here's what this means. So if you have a delta transformer or delta connected source, these are your three-phase terminals, right? What if one of these fails? One of these fails, and I remove this. What happens? Do I still get voltage between these two terminals, and these two terminals, and these two terminals, or not? Yeah, I still have a voltage between these two terminals, and I still have voltage between these two terminals, and I still have voltage between these two terminals, right? So, but of course, so the nice thing about the delta transformer in a high reliability or a, high power application is that fine. Even if one of these dies, I can still use it. But of course, power is equal to what? 3 V phase times I phase, right? And this will never change, right? And I lost one, right? So I will, power is reduced. So I will operate with a reduced power, but I can still operate the delta transformer even if one of the delta transformer, one of the phases fails, right? So that's a advantage of a delta to delta type transformer in a high reliability or application, which is typically not found at low voltage. You will typically find it at medium and high voltage, right? So generating transformers sometimes will be, generating transformers are delta connected, and you may find them, based on 3 single phases, so that if one fails, they can remove it and put back one into the system, and they operate at a reduced power for a while, right? So that's one point. Okay, so the American standard for marking three-phase transformers utilizes H1, H2, and H3 on the high voltage terminals, and X1, X2, and X3 on the low voltage terminals. That's why if you go back to the nameplate that we used before, there were lots of H's and X's. It's because the standard dictates that you use H's on the primary or the high voltage side, and X's on the low voltage side for the different phases. And we will typically use this, or we will typically use, the capital letters on the primary side for the high voltage and lowercase for the low voltage side. That's one thing related to the standard. The other thing related to the standard we will see here on this slide. So the phases of a star or a delta transformer can be labeled so that there is no phase shift between the corresponding quantities. What does this mean? I think we also touched upon this before, where I said that whenever we draw these transformers, we will draw them such that we go back to our single phase equivalent of the transformer. We said that if the dot notation on the primary and the dot notation on the secondary is in this fashion, and current is coming in on the primary and out of the secondary, then this is the basic building block of the transformer that we talked about, where we have V here and E here, V1, E1 here, developed due to that, and then we have a terminal voltage V2 here, as well as a voltage E2 that's generated across this winding. And we said that it's the same flux that is generating both voltages, right? So since it's the same flux that generates both voltages, E is equal to N d phi by dt. If this flux is a sine, this is a cosine, right? And they are both cosines. The E1 and E2 will be in phase, and they are both 90 degrees leading the flux, and we drew the phasor diagram for those, right? So any two windings are in the same core with the same dot notation. So if the current polarity is in this fashion, then the voltage in the primary and the voltage in secondary are in phase. If I flip the dot, then they are 180 degrees out of phase, right? So if I flip the winding the way I've wound the transformer such that the current flows out of this winding, then the voltage also polarity will be flipped, right? So, but it's either in phase or 180 degrees out of phase, as long as they are on the same core, right? So when I draw a star transformer, any two windings that I draw in parallel, I will say that they are on the same core, right? So these windings, these two are on the same core. So I took a single phase transformer. These two are on the same core. These two are in the same core, and these two are in the same core. So the voltage on this phase A versus this phase A is in phase. This phase B in phase. This phase C, they're in phase. Right? And I created this transformer by taking 3 of these single phase transformers. I'll show a figure later. I just took 3 of these single phase transformers, I connected them in a certain fashion. So I have these 3 single phase transformers. And this is phase A, terminals phase B, terminal phase C, and then this is my neutral on the primary side. This is my neutral point on the primary side, right? And the same thing with the secondary. And I have a neutral point here on the secondary side. And whether I connect this to ground or not, this is not important in this chapter. It's more important when we talk about protection. So for now, this is how I can construct this transformer. And this voltage and this voltage are in phase as long as the dot here is the same as the dot here. So current is going into the primary here, current going out of the secondary on this top side as well, right? Then the voltages are in phase. Okay. Same thing with the delta, right? Exact same thing with the delta. If I would connect it instead of this way, I would remove this connection to the neutral and connect the 3 windings in series and create a delta. And I have a picture of that in the slides. And windings on the primary and the secondary that are on the same core are in phase, so that we will see that everything on the primary side and everything on the secondary side will be in phase. There's no phase shift. So if I ask you what is the phase shift between a load connected to, or a source connected to phase A and a load connected to phase A, there's no phase shift, right? The phase A voltage is in phase with the phase A voltage on the secondary side, right? So there's no phase shift between the primary and the secondary in a star-star or a delta-delta transformer, right? The trick comes into play when we have a delta-star or a star-delta transformer. Okay. For a star-delta or delta-star transformer, there is always a phase shift. So labeling the windings is going to be an important consideration. So there's a standard for that. The standard says, or the standard dictates that the positive sequence quantities on the high voltage side will always lead their corresponding quantities on the low voltage side by 30 degrees. Right? So I will explain this in drawings, but this is sort of the standard for connection of transformers. You always have the high voltage side leading by 30 degrees. Why is that? We will look at the connection right now. And this is for positive sequence voltages applied. So if I apply positive sequence voltages means what? Means I'm up, excuse me? Yeah, ABC means I'm up, if I measure my waveforms, I have phase A first, I see first A, phase A, then I see phase C, then I see phase B, then I see phase C. So I first see phase A, then phase B, then phase C. If I'm standing here and these are my phases, they're rotating, and in time they look like this. So this would be phase A, and this would be phase B, and then this would be phase C. Right? So A, B, and C. This is positive sequence, right? Negative sequence, it means that I see phase A, then I see phase C, then I see phase B. Right? I just flipped 2 wires. Right? So this is positive sequence, this is negative sequence. Right? So we will see that for the same transformer, if I apply positive sequence on the primary, I will get a certain phase shift on the secondary side. I apply negative sequence, I will get a different phase shift between what? Between the phase shift I'm talking about is, remember, everything we're trying to do is take our system and represent it as single phase equivalent circuit. Right? This is everything we're doing in this course. Taking this power system and trying to see how I can move it to a simple single phase equivalent circuit that I can solve. Right? So now if I apply positive sequence, I will get a certain transformer in my single phase equivalent circuit. And in a star-star and a delta-delta transformer, if I choose my ratio of the bases equal to the ratio of the terminal voltages, then I don't have a problem. The transformer will be eliminated. It will be a one-to-one transformer. Anytime you have a star delta or a delta star transformer, meaning a transformer that phase shifts the quantities on the primary with respect to the quantities on the secondary, you cannot eliminate the transformer. You cannot. You can eliminate the transformer's turns ratio by the same choice of base ratios. The ratio of the bases equal to the ratio of the terminal voltages. If you do that, you still eliminate the turns ratio that's in the system, the turns ratio that's in the single phase equivalent circuit. And I will show that what that means. But the phase shift will still be there. So remember what we were saying last time was, if I have a transformer and I choose my base voltage on the primary and the ratio of the base voltage on the primary and the base voltage on the secondary to equal my transformer terminal voltage on the primary, transformer terminal voltage on the secondary, what will happen when I draw the per unit equivalent circuit? This transformer becomes a one-to-one transformer, and I can eliminate it. Or if I'm including its impedance will be a series impedance here that I will see if I'm looking from the primary to secondary to be the same. Right? That's what we did before, right? What I'm saying now is this is still valid for star-star transformers or delta-delta transformers. Still valid. But what will happen now is if you have a system with a delta star or a star delta transformer, then I don't have only magnitudes that I have to deal with like I had here, right? It's not a simple magnitude anymore. I have a phase shift between the primary and the secondary. Anytime you have a phase shift between the primary and secondary, you have to account for that. So what we will end up seeing is that we will end up with a transformer in the single phase equivalent circuit. Even in the per unit single phase equivalent circuit, we will end up with a transformer. But this transformer will only have a phase shift, and this phase shift will follow the standard. So we said that the high voltage will lead by 30 degrees. So this phase shift, if we had properly chosen the bases, again, if you properly choose the bases, then you will end up with a transformer with a turns ratio of 1-to-1 as a magnitude, but there's a phase shift on the high voltage side with 30 degrees. So that's the high voltage side. So in this case, this is a delta star transformer, right? How about if it's a star delta? I will say that in this case it's e to the j30 to 1. Right? Star will always be the high voltage side. Okay? So this is what we're going to end up with in the per unit equivalent circuit. So everything on the anytime now you have to bring in currents and voltages from this side to this side, you have to phase shift them by 30 degrees. Anytime you have to bring currents and voltages from this side to this side, you have to phase shift them by 30 degrees. Right? This can also be written as what? Instead of 1 e to the j30, I can write e to the minus j30 to 1. Right? Same. Right? So the high voltage side leads by 30 degrees, depending on what you want to take as your reference. Right? So that's what we're going to end up. This is the conclusion of what we're going to talk about today. Right? So we're going to see the proof of it, and we're going to also see, okay, so remember what we did was we first solved our circuits not in per unit, right? We solved took our system and converted it to a single phase equivalent circuit, and we solved it not in per unit. So we will see what this transformer also looks like when it's not in per unit first. And then what I'm claiming is that, once you do the proper choice of base, then you can convert it to something like this. And it's simple to solve, right? You know how to solve this in your single phase equivalent circuit, right? You can move things, collect the impedances, move the impedance from the primary to secondary, secondary to primary, and then you still have to make sure that you deal with the voltages and currents. But the impedances, when you transfer them based on magnitude only. You will not change the magnitude of the impedance, the angle of the impedance, right? So that still the transfer from primary to secondary will be based on the turns ratio squared, right? We will see. I think when you solve the examples, it will be clear. Okay, so that's what we're trying to reach to. Okay, and then we will just give you the proof and solve some examples today. That's the objective of today's class. But again, this does not really matter when we are looking or interested in equipment ratings. So most of the time, I will tell you, okay, ignore transformer phase shifts, and we will solve the problem like we did last class. That's most of the time, because most of the time, what we are worried about, at least when we're studying power flow or load flow in a power system, is, okay, how is the city going to expand? How am I going to choose my equipment rating? For that purpose, I don't care about this 30-degree phase shift. So that's most of the problems you will see will be, okay, ignore transformer phase shift. But in order for you to understand that that this exists, we have to cover it, yeah, because it's very important when we talk about protection. Yeah. Okay. So as we said, Y-to-Y transformers, we have no problem with that, with them. Again, when you create a Y-to-Y transformer using 3 single-phase transformers, again, we drew it up quickly, but here it is drawn up again. And again, they drew everything, both the turns that are on the same core. So this is H1, this is phase A. Primary is labeled H1, the secondary labeled X1. So primary labeled H1, secondary terminal labeled X1. So they drew them in parallel because they are on the same core, right? So just complies with what we're talking about. And here the line voltages on the primary and the line voltages on the secondary are in phase, right? All the voltages are in phase. I mean, the phase voltages are in phase and the line voltages are in phase. But the line voltages are, of course, square root of 3 greater and lead by 30 degrees, right? So that's the relationship between line voltage and phase voltage that we talked about before. So any questions about the star-star transformer? Same thing with the delta-delta transformer. I don't know if I'm not sure if we have the figure for that in the slides. But the interesting part comes when we talk about the star-delta or delta-star transformers. Yeah. So for a star-delta or delta-star transformer, here they also drew the windings that are in on the same core in phase. So they didn't draw the connection of the transformer, but it's I think they drew it later. Yeah. I think they draw it later. Yeah, here. This is a star-delta transformer. So they draw it later. Yeah. So let's see how we derive the phase angle here. For positive sequence, this is the phase angle. Okay, so this is 3 single-phase transformers, and we connect them in star on the primary and delta on the secondary. So delta, so I have my terminal, my phase A terminal, phase B terminal, phase C terminal, right? My delta looks like this. Phase A, phase B, phase C, right? So I will come, phase A will be connected to some winding, and then the end of that will be connected to phase B, right? So phase A connects some winding, end of that connected to phase B, right? Phase B is connected on one side to that same winding that was connected between it and phase A, and then the other side connected to the terminal C, right? So that's this one here. And then C is connected one side to the winding between it and phase B, which is this. And then there's another winding between phase C terminal and phase A, right? So that's this one here. Okay, so this is the connection on the secondary side as a delta. Primary side is connected as star. So this is phase A, phase B, and phase C, and then the second terminal from each of the windings is connected to the neutral point. Okay, so it's star on the primary side here, and delta on the secondary side. Okay, and the dot notation is the same. So this is dot here, current coming in here, current coming out here. Dot notation is the same on all of them. We agree? So now what we're going to do, we're going to supply the primary with positive sequence, 3-phase balanced positive sequence voltages. Okay, so what does that mean? It means we're going to supply it with this phase A here, phase B, and phase C, right? This is phase A, B, and C. This is what I'm going to apply to my primary side, right? So I'm going to apply this here. So this is neutral point versus A. So I'm applying phase A in a certain polarity on this winding. I'm applying phase A on this winding with a certain polarity, right? I'm applying phase B in phase with my positive sequence diagram I have here. I'm applying phase C here, right? So I'm applying the voltages using the same positive sequence notation that I've assumed, or that I would like to apply, or I said I would like to apply on the transformer's primary, right? So in phase with this phasor diagram that I have here. Okay, this is what I have on the primary side. So what do we get on the secondary side? So to do that, we do the following. Okay, phase B, the B terminal is away from the dot, right? So okay, let's before I do that, do we agree that the voltages in the primary and the secondary will be in phase as long as the windings are on the same core? We agree with that, and the dots are in this fashion together. If the dot is flipped, then the voltages are also flipped. If the dots are in this fashion, then the voltages are in phase. So now what I did was, when I applied voltage in this polarity on the primary side, right? Then what I did was the result was on the secondary side I have voltage in phase with it. Correct? Forget about what the letters mean now, what the letters are right now. Just look at the voltage has to be in phase. All the voltage will be in phase. So the voltage on the secondary side here will also be in phase. Here will also be in phase. They're all in phase, right? But what are the terminals? What are the various terminals that we have? So to label the terminals and to know, if these are my A, B, and C terminals, okay? How do I know now the phase shift between the primary side and the secondary side? So the process is the following. First, okay, you draw them like this, because this is easy, but the homework you have a very complicated one. I don't know if even I can explain it without referring to the solution. Yeah. So anyway, you have these three voltages in phase. So what you do is the following. We applied the voltages such that we are applying positive sequence. So what we have is the A is here, the B is here, and the C is here. So the B is away from the dot. C is towards the dot, right? Let's look at these two for now. So the B is away from the dot, and C is away from the dot. So let's look at what we have on the secondary side. And we should do the same. So if I have B away from the dot, the B terminal away from the dot, then the B terminal should also be away from the dot on the secondary side. So I have the small b here. And C is towards the dot. So C should be also towards the dot on the secondary side. Okay? And then this phase voltage is between terminal C and another terminal. What's the other terminal? A. So A, you put A here. Same thing with this. This phase voltage is between what? Terminal B and terminal C. So I put B here already, then what I have here is C. Here, this side here, I have what? This side I have what? CA. So I expect to see what? A here. A here is the same as A here, right? It's at the terminal. So this is my terminal with the dot. This is my terminal with the dot. So the A will go here, A will go here. And the other one will be this is a voltage between, this is a winding between terminal A and B. So the other side of it is B. So these are my terminal labels on the secondary, and these are the terminal labels on the primary. So on the primary, these terminal labels correspond to a positive sequence voltage. So on the secondary, what do these correspond to here? This is BA, right? This is A and then B that I have here. And then this is CB, right? And then CA is this way. So if I draw CB like this, right, then this is CB, and then this is CA. Right, so I ended up with a delta on my secondary as expected, right? So this is my phasor diagram for the voltages on the windings on the secondary side. Okay? What did we want to do? We wanted to, again, what we want to do is take this and convert it to a single phase equivalent circuit, right? So it's like taking this and converting it into a star. So it's like taking this delta and connecting a star across it and seeing, okay, what's the phase voltage across the corresponding star that will be placed across this delta of the transformer, right? So that is like, okay, taking my delta here and connecting a star transformer to it, or a star load to it, and I would like to convert the voltage on my delta to my single phase equivalent circuit in star configuration, because remember, I cannot use a delta in my single phase equivalent circuit, so I have to convert it to the corresponding star. For impedances, it was easy. Take your voltage and take your impedance and divide it by 3, right? For voltages, we have to look at the phase shift and the square root of 3 value that we have between the star and deltas, right? So I have my delta voltage here, right? This is CA voltage. The CA voltage is applied across this phase and this phase of the delta of the corresponding star, right? I just want a single phase equivalent circuit, so I only want one of these phases, right? So this voltage here is applied across these 2 phases. It's like having a fictitious neutral point here, right, and drawing a star voltage this way, the 3-phase voltages on the star in this fashion, right? This line-to-line voltage, right? This line-to-line voltage CA, this line-to-line voltage, right? This line-to-line voltage here is applied across this phase and this phase, this phase and this phase, right? The sum of these 2 phase voltages is this line voltage that I have here, right? So if we now look at what the relationship is, so this is phase A voltage. This would be my phase A voltage. So now I want to see what the relationship between my phase A voltage, VA on the secondary side, right, with my VA on the primary side. Remember, I'm trying to draw my single phase equivalent circuit. So my single phase equivalent circuit, I have, let's say I initially have a generator on my primary side, and my circuit looks like this. I have a generator and a transformer and a load. And this transformer is a star delta. It happens to be a star delta here, right? So what I would like to do is draw the single phase equivalent circuit. So I will draw the generator as a source, right? Can I erase this now? I will draw the generator as a source, and then I want to draw the transformer. I cannot eliminate it here. I will either, in the best case, I will end up with a phase shift, right? And then I will have my load. This is what the circuit will look like. And high voltage side will lead by 30 degrees. So this would be e to the j30 to 1. That's the end result, right? But how did I come up with this e to the j30? The e to the j30 came from this phasor diagram. Let's see how. Okay, so this is the phase voltage on phase A of the secondary side. I have to see what phase voltage, what is the relationship between its angle and phase A voltage on the primary side. Remember, this is phase A voltage on the primary side supplied by the generator. It goes to the transformer. Transformer secondary side is phase shifting the input, right? It has phase shifted the input with respect, it has phase shifted the input with respect to the output now. The output where? The output as a single phase equivalent star of the delta secondary of the transformer. Confusing, right? So So here, the transformer secondary side is a delta, right? The transformer secondary side is delta. But the terminal voltage is between these two, right? This is my AB voltage. I don't care what's happening inside the transformer. What you do is you're measuring the terminal voltage of the transformer. You measure the terminal voltage of the transformer, and you measure the terminal input of the transformer. Remember, if for a star or a delta transformer, okay, VAB, line to line voltage in the primary, was in phase with VAB on the secondary. But here, you measure VAB on the primary, and it's not in phase with VAB on the secondary. It's not. It will not be in phase because you have a delta transformer. So as soon as they're not in phase. Why is they're not in phase? Because I connected it in a different way. If I had connected this in a star configuration, then the voltages would be in phase, and here I would have what? I would have N. This one would be what? Would look like N small a. This will look like N small b. This will look like N small c. Let me group these into one phasor diagram. Okay, this is my N. I have C here, A here, and B here, right? So in this case, this is my phase A voltage on the primary side. Phase A voltage on the primary side was this. This is always the primary side, right? This is my high voltage primary side. Then my secondary side was A here, then B here, and C here. This was my phasor diagram of the secondary side terminal voltages that I have. This is what I ended up with. But because of the way I connected the transformer in a delta configuration, the labels on the windings are now different. So I measure the voltage between the line to line. It will not be in phase. I have to now take this line to line voltage that's not in phase and figure out the corresponding single phase equivalent circuit. What will it look like? So what I know about the fact that what's inside is that it's a delta. This delta, I take it and connect it across an equivalent imaginary star. And then I look at the phase voltage across phase A on this imaginary side. And that voltage is what I will put in my single phase equivalent circuit. Right? That's the voltage I want to put in the single phase equivalent circuit. And that's the voltage that will dictate this e to the j30. I know it's going to be 30 degrees now. Okay, we know that. But where did that come from? It came from here. Let's look at this. Let's look at this phase angle. Now the phase angle, this phase angle here with respect to the reference. Reference is 0, so the reference is the horizontal. And reference is the horizontal. So this is, my primary was at a 0 degrees, was my reference. My secondary was what? My phase voltage on the secondary was lagging by 30 degrees. Right? Now, does this make sense? Remember we said that the high voltage, the star side, will always lead by 30 degrees. So now, yes, it makes sense. The phase voltage on the secondary side, which is the phase voltage on this fictitious star load that I'm going to use in my single phase equivalent circuit, is lagging by 30 degrees. And that's what we have here in this triangle. So that's where this 30 degrees comes from. Okay? At the end of the day, really, if we're just delta star transformers, you will just automatically, okay, e to the j30 on the high voltage side, on the star side, and 1 on the other side, when you convert everything to per unit. But where did it come from? And now, if you want different phase shifts, how do you derive that? You go through this process. Okay, you label, you put your voltages here on the primary side, and okay, this one is away from the dot, this one is at the dot. You label them this way, and then you build your output voltage phasor diagram on the secondary side, and then you look at the relationship between phase A on the primary and phase A on the secondary side, and that's the phase shift. So in one of the problems in the homework, I believe they ask you for different phase shifts. Okay, I want a phase shift of 90 degrees, or what phase shift does this transformer create, or something like that. Yeah. Okay, so now this is, and then now let's look at what happens when we keep the same transformer, but I will apply negative sequence. And you can look at problem, last at the end of the chapter, the last set of problems. They will have pictures here. pictures of transformer windings. Okay, so we applied positive sequence and we derived where this 30 degree. How about if we apply negative sequence? That's what we have. We apply negative sequence. So let's go through this again. So positive sequence is A, B, C, right? Negative sequence is A, C, B, right? So I apply this negative sequence now to my primary side. So this is still a star delta transformer. And these are my terminals A, B, and C. I think in one of the problems in the text, they tell you, no, this is A, C, then B. What is the corresponding phasor diagram? Right? Right? So let's go through the logic again, right? So this is my primary side. It's connected in star. I apply negative sequence in this case. So and neutral is here, A is here, and then C. So on this phase A, neutral is to the left, A voltage to the right. And then on phase B, it is in phase with this phasor diagram, with this phasor that I have here. So this is neutral B, and then neutral C, right? So this is what I have on the primary side. This is what I've applied. And we would like to know what is the phase angle between the phase voltage on the secondary side and the phase voltage on the primary side. Basically, what is the secondary voltage of the transformer that you're going to put in your circuit? You're gonna this transformer will always be represented as single phase equivalent in a single phase equivalent transformer. In a single phase equivalent circuit, the transformer will be a transformer. If it's in per unit and you properly chose the base and it's a star or a delta, it's eliminated. You eliminate it completely. If it's a star delta transformer, you cannot eliminate it. It will be there, and it will be represented as using a phase shift if you properly chose the base. Okay, so we will. I mean, I don't know too many ifs and thens, but when an example comes, it will be easier. So, but how you choose e to the j e to the angle is what is based on the connection of the transformer. Okay, so all transformers will be reduced to a single phase transformer by properly chose the base. Properly choosing bases is easy. You choose the ratio of the bases equal to the ratio of the terminal voltages always. If it's a star, delta, blah blah blah. Anytime you want to convert to per unit, you choose the ratio of the bases to be equal to the ratio of the terminal voltages. And then for a star delta or delta star, you have another problem, which is the angle. What is this value of angle? The value of angle depends on the details of the application. Okay, I'm applying positive sequence on the primary side and it's connecting the transformer in this way. Oh, I'm leaving the same transformer, but I'm changing the sequence on the primary of the voltages, and I'm applying negative sequence. This will change this thing. The e to the j 30, it may be e to the j minus 30. Okay? So this is still a star delta transformer. Same transformer. But I applied negative sequence. So now let's see what will happen. So here, C is away from the dot. So C is away from the... So we draw these voltages in phase with these voltages first. Right? We draw all the voltages in phase with each other. And then we have to label the voltages, the terminals on the primary side. So I have C away from the dot. So C away from the dot. What is the other terminal? This winding is between C, this is phase C here, and what? And A. So one side is C, one side is A. Here, I drew the voltage in phase. B is towards the dot. Right? So B is here, the one at the top here, towards the dot. This winding is between terminals B and C. So C is here. Same thing here. A is towards the dot. Or towards the winding. Sorry, A is here. A is outside. Sorry, A is towards the dot in here, or towards the winding. Sorry, towards the winding here. It's a bit confusing with the one in phase exactly. So these are in phase, and the winding is between terminal A, right? Terminal A and terminal B. How do you select which one is A, which one is B? Let's find a nice way to do it. I would do this. I would draw here. I have my C here and A, right? C and A. This is defined by this one here. And then I have my C here and B. So I have to start from C, right? And go to point B, right? So I ended up with my AB being this way. So which means that these are labeled this way. Okay? So the delta now looks like this on the secondary side. Same process, right? This delta, I have to connect it to a fictitious star load, because a star is what I can take to my single phase equivalent circuit, which is like having a neutral point inside this triangle here, or this phasor diagram. And the objective is to look at the phase angle between the phase voltage on the primary, phase A voltage on the primary, and phase A voltage on the secondary side. So say phase A voltage on the primary is here, right? It's still with the horizontal, right? And phase A voltage on the secondary side is here. It makes an angle of 30 degrees leading with the horizontal. That's what you have here as well. Okay? So this is a star delta transformer. So even though this was my high voltage side, we ended up with this. Now, remember, I'm drawing my single phase equivalent circuit. In the single phase equivalent circuit, this side is leading by 30 degrees. This side is now leading, this phase voltage on phase A here is leading phase voltage on the primary side by 30 degrees. Even though this is a star delta transformer and the star is the high voltage side. But because we said that when we apply negative sequence, the negative sequence phase shift is the reverse of the positive sequence phase shift. The high voltage side lags by 30 degrees in that case. Okay? Is it clear? Yes? So are you okay with how to draw these phasors? Or you want to go through it again, or no? You're fine? Okay. So yeah. So now we looked at phase shifts, right? But turns ratio also plays a role, right? So here we looked at phase shifts, and we said that if I properly choose the ratio of the bases equal to the ratio of the terminal voltage, then the transformer will, the transformer in per unit will look like a 1 to e to the j 30, or 1 e to the j minus 30, or e to the j minus whatever angle, or plus whatever angle, right? Depending on the phase shift of the transformer that you've created. That's when you convert per unit and you properly chose your base, right? But in reality, of course, if you look at a star-star transformer, then the ratio of the voltages, the terminal voltage, will tell you what the turns ratio is, right? For a star-star or a delta-delta transformer, if I look at the voltage, just measure voltage in primary, voltage in secondary, I can tell you then the ratio of the turns on the primary and turns in secondary is a certain value. With a star-delta transformer, it's not the case, right? Because with a star-delta transformer, I already have a magnitude change because of the square root of 3. Right? I already have a square root of 3 between the star voltage and the delta voltage, star voltage, phase voltage on the star, and on the voltage on the star on the delta side, because it's a line voltage in that case, right? So how do you account for that, right? So what we will see here is the following. The way they do that. So for a star delta transformer, the ratio of the turns is equal to the ratio of the phase voltage on the primary, right? So the phase voltage on the primary, and remember, this voltage is in parallel with, this winding is in parallel with which winding? The one we drew in parallel with it, right? So this winding is in parallel with this winding. So the phase voltage on the primary is in phase with a line voltage VAB on the secondary side, which is the delta in this case, right? So that's the phase voltage on the primary and the line voltage on the delta side, VAB, right? So that's the ratio of the turns in a star delta transformer, right? In a star star, it's the ratio of the same voltage. So it's either the phase voltage on the primary, phase voltage secondary, line voltage primary, line voltage secondary. The ratios will tell you what the turns ratio is. But in a star delta transformer, it's not. It's the ratio of the phase voltage on the primary and the line voltage on the secondary, right? This is the phase voltage on the primary, and it's on the same core with this winding, and this winding is actually producing the line voltage VAB on the secondary side, right? So this is the voltage, the line voltage on the second. So that's why in a star delta and delta star transformer, the turns ratio does not, the terminal voltages, the ratio of the turns voltages, terminal voltage is not the ratio of the turns of the transformer, right? And then when we want to draw, so I cannot just take that, the star delta transformer and draw a single phase equivalent and put n primary and n secondary on the single phase equivalent circuit, right? So for a star star or a delta delta transformer, I can draw my single phase equivalent circuit of the transformer and put n primary here, n secondary here, right? That's what we were doing before, and this is valid for star star or star delta or delta delta transformers, right? Now I cannot do that because I can find these numbers from the voltage here versus the voltage here, or if I have the voltage here and the turns ratio, I can get the voltage here, right? Or if I have these two voltages, I can know what the turns ratio is, so on and so forth. But for a star delta transformer, we said that there's a phase shift that you have to consider, and we derived the value of the phase shift was just 30 degrees for positive sequence. So this is a star delta transformer, so this is the high voltage side, and this is the low voltage side, right? So we expect to see that the high voltage side will lead by 30 degrees. So the new turns ratio, right, we have another turns ratio now. The new turns ratio is not pure voltage ratio or just a real number anymore. It has the effect of this delta transformer in there considered. So we had our delta, we converted it, remember we connected a fictitious star across it. We had our delta, we connected a fictitious star across it. We took this voltage on the delta, on the transformer, and said, okay, what is the corresponding voltage on the phase of the star? The corresponding voltage is going to be phase shifted, and the magnitude will be less by 30 degrees, right? So the magnitude of this voltage is less by 30 degrees with this voltage, with respect to this voltage. And the phase angle between this voltage and this voltage, the phase shift between them is 30 degrees, right? So that's what we derived when we were looking at the diagram in a little bit. So now when we draw a transformer, this is not in per unit, right? This is before we go to per unit. Remember before we read the problem and draw the impedance diagram or the single phase equivalent circuit with real values, right? In here we will still have the transformer with its real turns ratio, but now the real turns ratio is not a pure number for a star delta transformer, right? The following step after that is to convert it to per unit. In per unit it's easy actually. In per unit, if you properly chose your base, then the transformer, the star delta transformer, as we said, will end up being nothing but like a simple single phase equivalent circuit transformer, 1 to the e to the j, whatever the angle is. That's after you convert to per unit. Before you convert to per unit, you will have to see what the actual turns ratio is. The actual turns ratio is not numbers anymore. It's numbers and an angle, right? So this numbers and an angle depends on is what this T, this new turns ratio is. This is the actual circuit before converting to per unit, right? So the T, the new turns ratio in a star delta transformer is the turns ratio between what? The phase voltage on the primary, and remember that we were trying to look at the single phase equivalent voltage on the secondary side. So it's the phase voltage on the primary and the single phase equivalent voltage on the secondary side. So it's like taking a delta and connecting a star across it, right? So what is the ratio between these two? The ratio between these two is what? So remember this, if we have some voltage on the primary side, what voltage do I have here on the phase? Yeah, which voltage is higher? So remember this line voltage is coming from my star on the primary side. This is so I have a transformer and a fictitious load, right? The transformer has a phase A voltage, right? And the fictitious load has a phase A voltage as well, right? So I would like to do what? I would like to know what the relationship between these two quantities are. The relationship between two quantities are, there is a phase shift that we derived before, right? There is a phase shift between the quantities that we derived before, and that is 30 degrees. 30 degrees, what leads by, what is leading? The primary is leading by 30 degrees, right? Remember, this phase voltage is in phase with this winding. I mean, I didn't draw them in phase, but it's in phase with the corresponding winding in the secondary. This corresponding winding in the secondary has a fictitious star load connected across it. It's like doing what? Remember, it's like now the relationship between the phase voltage and line voltage of a star. This is the phase voltage of the star, and this is the line voltage of the star. The line voltage of the star happens to be the phase voltage of this transformer, the winding voltage of the transformer, which is going to dictate my turns ratio. Right? The turns ratio is dictated by what? The winding on the primary versus the winding on the secondary side. Right? So winding on the primary is here. This is my winding on the primary. Between it and the winding and this winding, there's a turns ratio, pure turns ratio, right? But I'm not interested in the voltage or the pure turns ratio between it and the winding on the secondary side, because what my concern is the single phase equivalent circuit. So I have this transformer now connected to a fictitious load. I would like to see what is the voltage on the single phase equivalent circuit that I want to replace in my equivalent impedance diagram for the system, right? So here between this winding and one winding here, there's a turns ratio. This turns ratio is equal to what? Is equal to the primary turns over the secondary turns. This one has NP turns. This one has NS turns, right? So it's fine. I have these they're on the same core. I have NP on the primary and S on the secondary, right? I don't care how it's connected yet, right? How they're connected, I don't care yet, not yet. So first I want to see, okay, the relationship between this one and this one is NP over NS, right? Now I want to draw my single phase equivalent circuit. So I want to take this voltage that was converted here from my primary side. So I have a voltage to convert it to the secondary to convert it to here. So I have a phase voltage here, right? I have a phase voltage applied on one phase of the transformer, right? This has a corresponding winding on the secondary side. This winding on the secondary side, the relationship between them is what? This is NP, this is NS, right? This is NP and NS. So the relationship between these two is NP over NS, which is the relationship between one phase of my star and one phase of my delta, right? That's the relationship between them is only the turns ratio. But I want to draw my single phase equivalent circuit. I want to remove this delta. For me to remove this delta, I want to see how this delta affects, or what this delta voltage corresponds to in a single phase equivalent circuit. So I take a fictitious star, I connect it across that delta, and I see what this voltage produces on that single phase equivalent imaginary star. Does it make sense? So basically now I want to take this voltage, that is my line-to-line voltage on the delta, and apply it to a star, an imaginary star, and see what's the corresponding voltage on that phase voltage of the star. Because that is what I need to draw my single phase equivalent circuit. So basically what I'm trying to do now is find the relationship between the line voltage of the star and the phase voltage of the star. Right? Basically that's what I'm doing at the end of the day. So the line voltage of the star and phase voltage of the star. This is my star with phase A voltage, phase B voltage, phase C voltage. What is the line voltage of the star equal to? VA minus VB. So VA minus VB. So minus VB is here, so I put it here. So this is my VAB. This VAB is actually what? It's actually that voltage that's applied on at the terminals of this delta. Right? So now what is the relationship between my phase voltage that I want to put in the single phase equivalent circuit, or this imaginary star that I put in here, and the voltage that was created by that delta? It's obviously less than it by square root of 3, right? And it lags it by 30 degrees, right? Or you can say it in another case, that the primary voltage is now leading by 30 degrees and square root of 3 greater than the secondary voltage, the secondary phase voltage, right? So, confusing. Okay, everybody's confused. Okay, so let me put a clean paper. Yes.
Right now, when you just said it lags the primary voltage by 30 degrees, do you mean like the fictitious Y load lags
Yes.
the delta by 30 degrees?
No, not lags the delta. Lags the star, the phase, same phase voltage. Remember, everything I want to convert to single phase equivalent circuit. So I want to convert this star delta transformer to single phase equivalent. This is my voltage, my primary, and this is my secondary. This winding and this winding are in parallel, right? So they're on the same core. I would say this has primary turns MP. This has secondary turns NS, right? This is physically what's there. If it was a star-star transformer, then the turns ratio, okay, now I want to let me draw my single phase equivalent circuit. I have to put something here versus here, ratio. I have to put a ratio. If it was a star-star or a delta-delta transformer, how do I draw my single phase equivalent circuit? I would just put NP, NS. That's if it was a star-star or a delta-delta, right? Because the voltages are in phase. So the phase voltage ratio of the phase voltages on the ratio of the phase voltage of the primary to the secondary is equal to the ratio of the line voltages primary to secondary is equal to the bases that I will choose on the primary and secondary. It's easy, no problem. And hence in per unit, now this is in actual quantities. In per unit, what is the equivalent circuit for this? Exactly, it's a one-to-one transformer if I properly chose my basis. And then it will vanish because it's a one-to-one transformer, right? So that's easy one. Now it's the star-delta transformer, which is a bit of a complication, right? So because I have the star-delta transformer, I want to draw my single-phase equivalent circuit. So I have to, okay, I'm producing, there's some voltage. I know that for a star, I can take one phase of the star and draw my single-phase equivalent circuit. So if I have, this is my one phase, I will take this one phase, and oh, wow, yes, I have MP on the primary side. Now I don't know what's on the secondary side. I have MP on the primary side. Secondary side, I have NS, fine, but is this in a star configuration? Or is this in phase with the primary? Because if I don't put a phase shift, that means that they're in phase, right? So if I don't put a phase shift in the turns, that means they're in phase. So this is MP, this is NS. Can I take a single phase here and draw? I cannot take a single phase out of the delta. I have to convert it to a single phase equivalent. For impedances to convert to star, we take the impedance divided by 3. But how do I deal with this? I have to figure out what the voltage is on the corresponding single phase load. I will create an imaginary single phase imaginary star connected load here, and then the voltage that I see on one of these phases, on phase A, is what I will have here, right? And that voltage is what? In this case, I took this voltage, the relationship between this and this is the turns ratio MP over NS. So there's definitely a relationship, NS factor in there, right? But what else? This voltage here is how is this related to the phase voltage on the secondary side? This voltage is actually the line-to-line voltage of a star. It's the line-to-line voltage of the star. So how is the line-to-line voltage of the star related to the phase voltage of the star? Root 3 and angle 30. Right? Phase voltage of the star, line voltage, this is A, B, C. This is phase voltage of the star, which is this. And line voltage of the star, which is this, or the voltage here across this winding. So the voltage across this winding is the voltage across this line. Right? In this case, it's this phase voltage and this phase these two phases have this line voltage across them, which is this line voltage is related to the primary phase voltage by the MP over NS. The relationship between the phase voltage on the primary, V capital A, and VAB. They are related by turns ratio. But I'm not drawing, I'm drawing a single phase equivalent circuit, so I can keep this on the primary side, no problem. But what do I do on the secondary side? I mean, there is NS plays a role, but it's not just NS anymore. I'm trying to draw the single phase equivalent circuit, so I need to look at the relationship between the phase A voltage on the secondary side and phase A voltage on the primary side. So now I have to find the relationship between these two, the line voltage here and this. The line voltage is square root of 3 larger and leads by 30 degrees. Right? So now the full turns ratio will have the effect of the turns ratio, the actual physical turns ratio of the transformer, as well as a square root of 3, as well as a 30-degree phase shift. Right? It is leading the phase voltage by 30 degrees. Right? It is leading the phase voltage by 30 degrees. So that's what we have here. It is leading the phase voltage by 30 degrees, and it's square root of 3 greater. So if I would like to find, remember, this is my phase voltage on the primary side. Phase voltage on the primary side is equal to the square root of 3 multiplied by the turns ratio multiplied by the phase shift. So that's the relationship between the quantities that we are interested in, which are this and this. Because that is the single phase equivalent circuit on the primary, single phase equivalent circuit on the secondary side. Is it okay? Again, when we do examples, I'm sure it will be clear. But, we did this. We talked about why bother with a delta before. Remember, we said that a delta actually traps current voltages that are in phase within the delta. They do not go out of the delta. I think if you go back and review, I think it was second video or something like that. So I'm not going to spend time on that. That's actually the most important thing. Delta windings can trap third harmonic currents in the system. So third harmonic currents are voltages that are in phase. You have 3 voltages that are in phase that are inside a delta. You have 3 voltages that are in phase. It's like having 3 DC sources. Right? These are 3 DC sources that are in phase. Right? The voltage polarity is the same. So these 3 DC sources, if you do KVL inside this loop, the sum of the voltages will be all 3 together. Right? And you have an impedance of 0 in this loop, so you have an infinite current in this loop, basically. So the third harmonic voltages are voltages that happen to be in phase. Because the third harmonic voltage of phase A is in phase with phase A. third harmonic voltage of phase B is in phase with phase B, right? But it's 3 times the frequency. So when you multiply it by 3, multiply the angle by 3, which is, phase A and phase B have 120 degrees between them. So you multiply the 120 degrees by 3, you will end up with a 360 degrees. So I drew it second video. I don't want to go back and spend time on it yet. But the idea is like the DC source. So here, even if I connect a load, current will flow on the loads. I connect the load, current will flow on the loads. Sure, but current will also flow inside the delta, right? So anytime you have third harmonic current, which is when we talk more about power system terminology, we will use the term zero sequence current. We will call it zero sequence current later. But right now, these quantities are in phase. These voltages are in phase. They will add up inside this loop, and current will flow. It will keep flowing. So anytime there's voltages that are in phase flowing in the power system, which is an example of that is the third harmonic, they will be trapped in the delta. The current will stay, these currents will flow in here, and the energy, remember, any waveform has a power spectral density, right? You're back to 314. You can take a waveform, do Fourier series, and each spectrum or each frequency, you have a certain power. So if I'm able to trap that current inside the delta, the third harmonic current inside the delta, and this delta has an impedance, this current will be flowing in there and burning up this impedance, burning up power in this delta. So I've consumed the power in the third harmonic that way, right? So that's one way, that's one advantage. The other advantage, what we talked about, this we will talk about when we talk about protection. And then insulation withstand is a disadvantage, actually, because a star has a connection to ground here, right? So you would have to remember each of these turns has a voltage with respect to each other. So, and when you E equals n d phi by dt, the windings on a transformer, each of them has a small voltage, and then the sum of all these voltages is the terminal voltage of the transformer. So each one has to be insulated with respect to the one next to it. But if you have one reference to ground, then the insulation there is low. And the one next to it also is very close to ground. So the insulation is low. Again, insulation depends on the voltage difference, right? So in a star, there's a lot of the 3 of the terminals are connected to a very low voltage, which is the neutral, which is theoretically supposed to be at 0 voltage. So the insulation required for these turns is low. In a delta, there is no winding turns that are close to 0 volts. So anything that happens, you may see full voltage across the windings, right? There's no 0 voltage. Here, there's a 0 voltage close to these turns, 0 voltage close to these turns, 0 voltage close to these turns, right? So the insulation required for a delta is typically more. So that's a disadvantage. The other 2 we will need to talk more about when we talk about protection. It will be more clear for you. So this is, again, delta Y delta, it's the same. The high voltage side leads by 30. And there's always the turns ratio and the minus 30 degrees. So now this is the relationship between primary and secondary. Primary here is a delta. So delta will lag by 30 degrees, and it is square root of 3 less voltage. Star was leading by 30 degrees, and it was square root of 3 higher voltage. So this T is the same basically, but the phase shift changes from minus 30 to 30. Yeah. What else? I think the next class we'll just do examples. Yeah. Yeah. The next class will be examples on this phase shift thing, and this is basically the end of the chapter. So we'll, I think, as planned, the exam will be on the 24th, because really the material we finished the material. We just have some examples to be doing in the next class.